Project 2. This is as part of CSE 564 visualization. The aim for the assignment was to do a data reduction and dimensionality reduction on any data set. So the requirement of the dataset was to start with at least 500 set of records and having at least 10 distinguishable features. So they could be both numerical or categorical. And the application had to be built on a client server system architecture. So for this, we were required to use Python Flask for as a server and D3 as a front end. Let me quickly jump to the code. So this is the code base. You can see on the home page, you can see the main.py file, which is the Flask app, and the index.html, which is the home page you load when you launch the application. And this is the D3 code for the application. Let me quickly launch the server. So this will give me an endpoint, and it's loading up a Flask server. So let me refresh this. The application is running on port 8888, and this is the drop down which lets you pick the kind of analysis you want to do. So for elbow plot analysis, here you see it's a representation of k and versus the eigenvalues, which is ideally the sum of squared distances within the k clusters. So we have picked a range of numbers for k, and we have come to realize that 3 seems to be an optimal number of clusters that are data can be divided into. And this is evident because the slope after this point, after this red dot, seems to converge, and it kind of gives an idea that 3 seems to be an ideal cluster number we can divide our data into. Coming to the scree plot, this is the plot that shows me all the components we have for a data set. So basically, since we had 19 features, these are the bars that represent the eigenvalues for the 19 features. And on the y-axis, you can see the combined explained variance ratio. So that is what we call the cumulative variance. The aim of this plot is to highlight how many minimum components we need to pick to get the maximum benefit out of the least components we select. So for the third component, we can see this is 1, 2, and 3. If we use these three components, just that out of the 19, we can be able to explain the 75% of explained variance. And similarly, for getting explaining the 90% of the variance, we can pick 6 to be an optimal number. So this is analysis on the original data, which is to find the intrinsic dimensionality and getting the optimal count for the components. Similarly, for random sampling, this is the sample we have taken from the entire data set, and it's a sample of size 300. So similarly, we have seen 75% could be explained using 3 components. Coming to stratified sampling, there's not much difference in the graph, but yeah, there's a technique difference in how we sample it. So this is done using k-means, and that is what we got from the elbow, showing third 3 clusters could divide the data set. So this is the 75% mark, and you can see that third 3 components could be ideally be excellent able to work on the data. Coming to PCA scatter plots, we have 3 different options again: the original data, random, and adaptive. So selecting the entire data set, we see the components being the data points being laid out across two most important components. So these are the eigenvalues which are being represented in the space, and if you hover over them, you can see the 2 most important components along with the eigenvalues. So one analysis you can make from this is that the most of the spread is along the x-axis. We can say that component 1 is a more definite choice over component 2. It's able to explain the data more clearly than the component 2. For random sampling, you can see there are fewer data points because this is obviously a sample of 300 points, and likewise, if you hover on any of these points, you can see the value of the selected samples getting the 2 most important feature values for the eigenvalues. Similarly, it's spread across x-axis, and you can see a huge bubble of dots on the left side and a small collection of dots on the right side. We can see it as a outlier for this data, uh, and you can just confirm it once more using the adaptive sample. So what's different in the adaptive sample is that you can see the different clusters clearly now with the help of colors. So this is the first cluster of components, this is the second cluster, and this is the third cluster. The representation is again more skewed and more spread across the component one, and we can see that the orange cluster is kind of shooed away and kind of acts like an outlier to us. For the MDS plots, we have two subtasks. We could use a Euclidean distance. So this takes a kind of a little bit of time because it needs to reduce n dimensions into 2 dimensions and has a lot of maths to do on the back end. So once it loads, so this is the MDS scatter plot for the Euclidean distance. This is on the entire data set, and you can see a lot of uh, circles here in the blue color, and all these are explained variances which are being aligned along more along the component 1 than the component 2, showing that the component 1 dominates over component 2. And similarly, we can see the values for all the eigenvalues of these data points. The sampled one should take a relatively lesser time. I hope it does. And yeah, so this is for the sample data of 300, and you see a similar spread of dots across the component 1 and component 2, and it's more varied across component 1 as it was in the previous case. Similarly, for adaptive sample, we could see actual clustering of the data points, and yeah, so blue, green, and orange are the three clusters as given by the k value, and this is the spread. Component 1 again leads over component 2 as clear from the spread of the data points. Second part was to analyze it using a different metric, which was a correlation distance. So for the original data, let's see, it should again take a little bit of time because of the computation heavy stuff in the back end. So this is the result of the correlation distance for the MDS on the entire data set. We can see there is an oval kind of an ellipse forming in the picture, and its this diameter is more along the x-axis, which is the component one, and we can see there's kind of symmetric representation of the data points in the form of an oval shape. We can hover over any of these dots, and just like previous cases, we can see the eigenvalues. For the randomly sample, we will should see a faster visualization. So this is the similar uh, way, but on the lower, smaller data set, and similarly on the component one, we can see there is a more varied explained variance. And this is on the stratified cluster, which we can see this is the one component, this is the second cluster, and this is the third cluster, and they're varied across component one more than the component two. Lastly, we come to the scatter matrix plot. So like all other things, we have for three subtasks, subdata. This is for the original data set. So this gives you 3x3 matrix, and starting on the three features, we had to calculate this using the top three components which we use from the square loadings. We have to sort them in the descending order, and this is what we got on getting the three PCA loaded attributes. The features were acceleration, jumping, and sprint speed. So the first plot, you can see it is as a distribution of acceleration and sprint speed, the comparison of jumping and acceleration, and this is acceleration against acceleration. Similarly, this is sprint speed versus jumping, jumping versus jumping, and so on. So obviously, for acceleration versus acceleration will be a straight line, and it clearly shows that the data representation is correctly done here. There is more spread of data across acceleration versus jumping, showing that there is a strong correlation in between these two components. Similarly, there is a linear increasing correlation between acceleration and the sprint speed. And you can also see there is a mirror image forming across left and right. So if you see, consider this as a mirror, you can see these two are similar and these two are identical and these two are as well identical. For the random sample data, we see minified representation in the similar fashion, just that the sample size is low, and you can see the three components being aligned and being compared against each other through the variance values. And lastly, this is for the adaptive. Let it load. Yeah, so this is a more neat picture for the same thing, and we can see the actual clusters here. You can see there are more green values than blue, and the least amount is the orange ones. So we can say that green and blue are the ones which are most important for our data, and so I think overall in strength would be green and blue, and the sliding tackle would be on the orange side. And similarly, we can say like there is a linear correlation. So if there is a more strength, we can say the overall component is also tightly correlated, and this is kind of a skewed like negative to positive, but as we go towards the right side, we can see the blue dots also moving upwards and showing the tight correlation among them. uh, Similarly, for the x equals to y line, strength versus strength will be definitely a strong correlation because it's represented against itself, so it has to be a full tight line. And similarly, we have the mirror image, and this completes my recording for this. I hope you like it. Thank you.